Before I start the lecture on Chapter 5, I want to go over one concept I did not cover in Chapter 3, and this is the idea of tonicity. Now, I know in your Chapter 3 quiz, you had a question on hypertonic, hypotonic, and isotonic solutions. And since I didn't cover that in lecture, you will all receive 1 extra credit whether you got the answer right or wrong. Now, let's look at this idea of tonicity. And tonicity deals with the ability of a solution to change the size and shape of cells by altering the amount of water they contain. And when we talk about tonicity, really what we're looking at is this idea of osmosis, because it's only the movement of water in and out of the cell, and that being the case, we need to have a semi-permeable membrane. All right, and so let's look at this first concept of isotonic. Here I have one cell. Let's say I have 4 glucose molecules inside of the cell. Outside of the cell, I have a solution that also contains 4 glucose molecules. Here's my before, here's my after. Okay, and let's say I add 50 milliliters of a solution that has the same concentration, final concentration of having about these 4 molecules that it's going to end up being bathed in. So here is my final. Still going to have the same ratio of inside of 4 glucose molecules, outside 4 glucose molecules. Dealing with osmosis, osmosis is only the movement of water. And so where's water going to want to go? Is it want to go inside the cell or stay outside of the cell? Good, it's both. Perfect. So if you gave the answer of both, you are absolutely correct. And so in this solution, what's going to happen, since water is going to go inside and outside equally, the cell's size, the shape, and the size will not change, and therefore that defines an isotonic solution. So size and shape of cells do not change. Now let's take this an example of a hypertonic solution. Okay, so in a hypertonic solution, here's my initial cell, and then let's say that we normally have it at rest, but we add a solution that has a higher concentration of ions. Let's say we have all these glucose molecules outside of the cell now. And then what's going to happen over time, right? So this is before, and this is after. What's going to happen to my cell? Is it going to stay the same shape and size? Is it going to get bigger, or is it going to get smaller? Perfect. It's going to end up getting smaller. So this is called a crenate shape, and this is kind of what it's going to look like. So here's normal, and because water is going to exit, right, water always wants to exit. It's going to get out of the cell because it's going to go towards this higher concentration. It wants to be where there's more of these solutes, and then because of that, the cell size is going to get smaller. Remember, most of these cells are composed of water, and so that's why it's going to get smaller. So we still have the 4 inside, and outside we have all of these cells. Okay, and that's why it gets smaller. Now, in college, the way I remember students would remember that is that if you imagine you as being water, so you are water, and each of these glucose molecules are parties. Do you want to be in an area where there's few parties or more parties? You want to be in an area probably where it's popping, right? Go to all the clubs. I don't know what the clubs are that people go to. I don't really go to that many clubs. Anyway, so you want to go out to where the poppin' places, right? Where the good music's at, where all the people you can check out are going to be at, right? And so you're going to be hyper people want to get out. I want to go out and explore all these other great places. So you being water, hypertonic, you're going to leave this cell, you're going to leave this area and go towards all this party area. Okay, and that's why this eventually gets smaller. Now hypotonic, oops, I misspell that. Hypotonic. In this situation, this is the complete opposite. So now let's say that our cell has lots of glucose molecules inside, but we only have 4 glucose molecules outside. Where is water going to want to go? Good, water's going to want to go inside of the cell because it has a higher concentration inside of the cell. And so over time, what do you expect the size and shape going to be in a hypotonic solution? Much larger, so much more spherical. And so here's a normal cell, here's a larger cell, so it's going to get big. So the way I remember this is a hypo hypotonic solution, this O becomes bigger. So hypotonic solution. Your cell becomes bigger because now all that water is rushing in. All right. So key things to remember: hypertonic, hypotonic, and isotonic solutions. Now let's start our Chapter 5 lecture, and we're going to go over the skeletal system. In this lecture, we're going to go over the different types of bones, and then also the composition of these types of bones. And then in your next lecture, we're going to go over the different bones itself. Okay, so let's get started. Now, what are the functions of the skeletal system? You may know a lot just thinking about it on your body. Okay, so one of the main important things is that it has support against gravity. So it's that nice attachment part for your muscles, and then also attachment part for your integumentary system. It also serves as a storage for two different things. We have calcium and phosphorus, so our minerals and ions. And this is also where we can store our adipose, or our yellow marrow. Well, yellow marrow is actually adipose. Okay, and this is going to be found in the internal marrow cavities. Another major function of the skeletal system is this concept of hematopoiesis. So hematopoiesis. Hemato deals with blood, and so this is where we produce our red blood cells. Okay, so not only red blood cells, but our white blood cells as well. Another major function is the protection of soft internal organs. And I want you to think about right now identifying a few of them. So what are a couple that you know? So think about your head. Great, so you have your skull protecting your brain. And what about your thoracic cavity? What do you have? Good, you have your sternum and you have your ribs, and all those protect your lungs and your heart. Okay, so a couple of organs there. You also have your pelvis, which protects, good, your bladder and your reproductive organs. And the final function of your skeletal system is that it allows movement due to attached skeletal muscles. Your ability to move only deals with the contraction of your muscles and then pulling on those bones. So it's this interplay between these two systems. Now, looking at the skeletal system, what else does it include? So we know the functions, but it includes your bones. It includes cartilages, all this connective tissue protecting the outside surface of your bones. We have joints, and joints are the areas where bones and bones come together. And then we also have ligaments. And ligaments, what these do are help join the bones together. Right, so you'll find all of these ligaments at these joints. Now, the subdivisions of the skeletal division, there's actually two, and so you'll notice them here by the two different colors. Here we have this blue region here, and this is called the axial skeleton. And what does it include? It includes the skull. It includes your vertebral column, your entire column here, your thoracic cage, both your ribs and your sternum. Now, the other division that we have is called the appendicular skeleton. And this deals with all of your appendages. And so that deals with your arm. This bone right here is the clavicle, the scapula, and then you have your legs, all those bones comprising your legs. Then you also have here your pelvic bones. Okay, and so all of these bones we're going to have to identify in our next video lecture, and you will also need to know all of these bones for your quiz and your next exam. And if you look at the bones of the human body, how many does our skeleton have in all? We actually have 206 all in all. And they're all composed of two different types of bone tissues. They're either kind of a combination of compact bone and spongy bone, or they can have one or the other. And so what compact bone is, it's a homogeneous, dense bone. So it's homogeneous, it's dense, and just like its name, it's compact. And so homogeneous, what does that mean? That means it's all made of the same composition, uniform composition. All right. The second type of bone tissue is spongy bone, and this appears like they're small needle-like pieces of bone with lots of open spaces. And so here, all of this is spongy bone. And just think about like a sponge for in your kitchen sink. It looks just like that, except much harder. Okay, so small needle-like. Pieces of bone filled with lots of open spaces. Okay. And so for this next couple of slides, we're going to look at the anatomy and structure of compact bone. Then we're going to delve into the spongy bone. And so looking at this compact bone, you're going to notice a couple things. Even though it is homogeneous, all of these homogeneous tissue is composed of all these structures we're going to see here. The first thing I want you to notice is we have all of these systems, these circular networks, spanning our entire compact bone. And these are all called the osteon, or another term for it is Haversian system. And so what this is a unit of bone containing a central canal. And what are these central canals? Well, all of these central canals found in all of these osteons have within it this arterial resource. And so what does it carry? Well, we can see here it carries this blood vessel. And why is that important? Well, central canal, it not only carries blood vessels and nerves, it also carries all these nutrients and oxygen through these blood vessels that are going to be needed to feed all of these cells found in our compact bone. So all of these that you see, all these little dots, all of these are our bone cells, and we're going to get into that. Now, also what you see, so our main arterial source for blood is going to come from outside of our bones. And because we just don't have this one arterial source, we need to have it to branch in order for it to get into all these bones here within these osteons. And so we have this branching part of this artery going through our osteon through the central canal, but we can also connect each of these central canals together by these lateral arteries called the perforating canals or Volkmann's canal. So two different terms for that. And so these are, once again, these are horizontal connections between each of these central canals. Therefore, they are perpendicular to the central canal system. So perpendicular to central canals, and they assist in connecting arterial supply to osteons from the major arteries. Arteries. All right, good. Other things I want you to notice here, we're going to take a closer look, is I mentioned we have cells found in these areas, and so I'm just going to make a little cross section just like that, and that's because this is where we're going to take a closer look in the next slide. Now when we take this closer look, I want you to notice these rings. Okay, so these are the rings that I'm talking about, and they're all alternating around this central canal. Here's the central canal. And what are these called? Are called lamellae. And these are those rings around the central canal. So rings around the central canal. And between these lamellae, I also want you to notice that we have this space here that's formed, and these are called lacunae. And these are cavities housing cells called osteocytes. And why are these osteocytes important? Because osteocytes, each of these individual cells here, here's the nucleus, these are bone cells. Okay. And so all of these bone cells are housed within all of these lacunae. And then if you also notice, we have these finger-like extensions that kind of span from one cell to the other. And so what are these called? These are called canaliculus or canaliculi. And the purpose of this is to connect all these nutrients and oxygen and ions coming from those arteries in the central Haversian canal, connect that from each of these osteocytes to the other as it is farther away from the central canal. Okay, so unlike those cells and tissues that we have in our skin, remember the farther away they get from our basal cell layer, the less nutrients they have. Here in these bones, we are able to give this direct blood supply, nutrient supply to these outermost cells because of smaller connections that are also perpendicular between the cells called canaliculi. Okay. Now, quick review. What are these structures called? So this center area here where this artery flows through is called central canal. Good. Here are all those lacunae housing our what cells? Osteocytes. And then this entire unit of lamellae and lacunae and our central canal and osteocytes is called osteons. Great. And this is a cross-section of our bone. Now, canaliculi, those are those tiny canals radiating from the center of our central canal to each of these lacunae. And once again, they are this transport system between nutrients in the Haversian canal to osteocytes in the lacunae. Now let's go over the second type of bone tissue being spongy bone. And if we take a cross section of spongy bone, I want you to notice one thing. Do you notice osteons? Remember osteons being those central canals in the middle, followed by all those lamellae surrounding it? No, we don't, right? We don't have any osteons. And why was that? Because, well, these osteons needed to connect all of these cells, osteocytes, to this central canal for that blood source. However, in spongy bone, we are actually bathed in a lot of spongy bone regions. This is bathed and surrounded by red bone marrow, which in itself is composed of lots of red blood cells, nutrients, and ions. And that being the case, here's looking at this cross section. I'm drawing everything in blue. This is all of that red bone marrow filled with nutrients and oxygen. All we have is simple diffusion coming from this outside going in through the canaliculi, connecting all of these osteocytes found in here. So we can then give all these nutrients to all of these osteocytes. Okay, so because of that, direct blood source, direct nutrient source, we do not have any osteons. We do have this branching network of bony tissue. These are called trabecules. All of that sponge-like appearance that you see. And yes, we do have blood production. However, not all spongy bone produces red blood cells. So not all but most. Okay. Now let's look at the different types of bones based on their shape, and then when we go through this, I'll also show you which marrows, which spongy bone do have those red blood cells that are being produced. So 4 different types. We have long bones. We have flat bones. So here's an example. We have irregular, and we have short. Okay. Let's go through these. Let's first start off with long bones. Long bones, structurally, they are longer than they are wide. Here's a perfect example, the humerus of our arm. Okay, here we have a long region compared to the width. Bone tissue, what are they composed of? They are composed of both compact and spongy, depending on whether we're talking about this long part or the ends of the long part of the bones. Location, where are they found? Mostly the bones of the limbs, so comprising majority of our appendicular skeleton. And that is my dog, I'm sorry. He probably sees a cat in the backyard. His name is Robbie, by the way. Except for our wrist, ankle, and our kneecap bones. Robbie. Another examples we just looked at here, the humerus, but also the femur. So here's that femur comprising our, what we could think of as our thigh bone. Also we have the radius. Radius, I just always remember being the one that's most distant, so longest radius. So if you put your hand in anatomical position, it's the bone that's facing the outermost, most lateral. And then here we have our, so that's the radius. And this is the ulna. Here we have 2 other bones. This one, it looks just like the letter T, that's how I always remember it. And this is a tibia. And the smaller one over here is the fibula. And so for those of you who love drumsticks on the chicken, that's what I love. If you never notice that there's a little thin bone that's always left, that's the chicken's fibula. Anatomy of a long bone. This shaft and long area over here, this is called the diaphysis. So for each long bone, we only have one of those. And then on either side, we have the epiphysis. And so that's this over here. Proximal means closer to your body, so this is the region that's closer to your body. Distal is away. So we have the proximal epiphysis and the distal epiphysis. Okay. So location, this is the shaft, and this is the ends of bones. Now this middle area, the diaphysis, this is all composed of compact bone, as you can notice here. At the epiphysis, we have a thin layer of compact bone, but majority of this is going to be spongy bone. So compact and spongy. Looking at the marrow, here we notice we have yellow marrow in the diaphysis, so we have yellow. And this is found in adults. And yellow marrow, this is really adipose. And I know sometimes people like eating the marrow of, what is it, like cows, or I don't know if they eat it of pigs, but of cows, I think, all that yummy, delicious stuff. So that's all the fat that they eat. Marrow, this diaphysis can also be red bone marrow in infants. And so as infants, all of our red blood cell production is actually found in here in the diaphysis. And then now as adults, our marrow is red in our spongy bone. And that's where our red blood cell production occurs. Okay. But of course, it's not uniform everywhere, and the distribution isn't everywhere in the body. However, for the most part, I just took this offline, just kind of get an idea and sense of where do you find this red bone marrow. And so here we have this proximal epiphysis of our femur. Also the proximal epiphysis of our humerus. That's where we're going to find our red blood cell production and the red marrow. And eventually when we see the other types of bones, we have flat bones, and that's where we're going to see a lot of the red blood cell production. Also our vertebra, vertebral column, all of that irregular bone, lots of that red blood cell production. Okay. More anatomy of this long bone. If we look at this, outermost covering, we also have this composition of bones being of a connective tissue. And so periosteum is this fibrous connective tissue surrounding our bone. And what holds that in place to our bone itself are all of these fibers called perforating or Sharpey's fibers. Now we also have that major nutrient arterial supply entering outside of the bone and then going into and splitting into our our Volkmann's canal and our central canal to feed all of our osteocytes. And so I did mention to you a chicken. That's a great way to look at these different structures. If you ever want to take apart a drumstick, let's go to KFC. Okay, and then you'll also notice, I don't recall, I think it's down here. No, I'm sorry, it's up here. Once you eat away at the chicken, you're going to notice there's this little hole on one side, and you can notice the arteries, one artery going inside of there. Okay, so that's the major arterial supply feeding the entire bone. And then also that little bone I was telling you about earlier, and that looks kind of like a toothpick, that's the fibula. Okay. More anatomy. Okay, so here we have connective tissue surrounding majority of that diaphysis, but at the ends of our long bones at our epiphysis, we're going to notice we have articular cartilage. So these are only at the ends of the long bones. And this is all composed of hyaline cartilage. And why is that important? Because this allows reduction This reduces the friction as these joints come together and allow for movement. Right, so very different from our diaphysis. Now also, if we take a closer look of our bone, we're going to notice this region over here. And depending on whether we're talking about an adult or a child, this is going to be different terms. And so first, what we have as, Okay, so epiphyseal plate. What an epiphyseal plate is composed of hyaline cartilage. So this area over here, if you imagine being composed of hyaline cartilage, this is found in a child. And really what happens here is with this cartilage can be replaced by bone, specifically hyaline cartilage. So over time, this can be replaced by bone. And this eventually will give rise to the elongation of our bones. And this is why it's so important during puberty. We have growth hormones start stimulating all the hyaline cartilage found over here, and then eventually it's going to get replaced by bone, and then over time that's how we get our growth spurts, and that's how we get our height. Okay, and so we find that in children. Now over time what happens? Well, we start reducing our hormones production for puberty, our growth spurts, and over time this hyaline cartilage turns ossified, so it turns back into bone. And so that becomes an epiphyseal line. So epiphyseal line are found in adults. So you as an adult have an epiphyseal line. And this is just a remnant of an epiphyseal plate. Epiphyseal plate. So it's ossified. Right? And so for people, after being an adult, if anybody takes growth hormones, really you're not going to get taller because now we don't have any more hyaline cartilage. What happens though is because if you do take growth hormones, what can happen is that you don't have longitudinal growth, but you grow side to side, and this is called appositional growth. So these bones can become much wider. A couple of diseases is something called acromegaly. If you guys know, what's the guy's name? The one who played Jaws in the old James Bond movies. He had acromegaly. So it's a really elongation and enlargement of, I'm sorry, not elongation. It's appositional growth and enlargement of your bones. Next type of bone we have short bones, and these are cuboidal shaped. And it's mostly composed of spongy bone. However, the outermost layer is compact, but inside is all composed of spongy bone. And these are located in the bones of your wrist and your ankles. So these bones over here and these bones over here. In a couple of examples, we have carpals. So the wrist ones, these are called carpals. And the ones comprising our feet, are the short bones of our feet, these are called tarsals. Tarsal bones. Next category we have our flat bones. These are thin, flattened, and usually curved bones. They're composed of both compact and spongy. In which case you have the spongy bones sandwiched between two layers of thin compact bones. And we'll see this where? In our skull, our ribs, and our sternum. A couple of places. And then finally our last classification is irregular bone, and these ones just do not fit any category or bone classification that we covered so far, and they're irregular shape. These are also composed of a thin layer of compact bone, but majority of it is going to be spongy. Now examples we have our vertebral column, of course, so each of these vertebrae. And we have our hip bone, which we call our pelvis bone. Now let's go over the formation of bones. We're only going to focus on how long bones are formed. And as I mentioned earlier, there is one specific type of cartilage that can be replaced by bone, and that is, good, hyaline cartilage. And hyaline cartilage we're always going to find at our epiphyseal plate. And so here is in a child, we have this epiphyseal plate. That can be replaced by bone, and by doing this we allow for longitudinal or appositional growth. Good, we allow for a longitudinal growth. Now what we're going to notice, and as you can see, the stages from an embryo all the way to a child, we're going to eventually replace all of this hyaline cartilage with bone, and new cartilage is continuously being formed. And all this older cartilage that was present is eventually going to become ossified, meaning turned into bone. And so let's start over here. Stage 1 in an embryo, bone's going to start replacing all of this cartilage. And so the cartilage is going to start breaking down. So step number 1, cartilage will break down. Be replaced by bone. In the step 2, in a fetus, what happens? Well, all this enclosed cartilage that was right here in the middle is going to start becoming digested away. And what's going to end up forming is this medullary cavity. Now, what can also happen is if there's a new arterial source feeding in new bones, then this can also be a new regenerative center in order for us to replace more cartilage with more bones. And so we have form 2. Now here, eventually we have complete ossification of our medullary cavity, and we still can allow for more longitudinal growth. Because we have the epiphyseal plate. Perfect. And now the ability for your cartilage to become replaced by bone is by the action and also the breakdown of more bone. This is by the action of 3 different cells called osteoblasts, osteoclasts, and osteocytes. Before I go over the role of these 3 different types of cells, I want to go over how they're important for this concept of remodeling. And what remodeling is continuous breakdown and reforming of bone tissue. And this can occur in response to 2 different factors. The first is the calcium levels within the blood. And the second is a pull of gravity and muscles on the skeleton. I want to go over this first concept, and that's the idea of blood calcium levels, and that the skeletal system is very involved in maintaining calcium homeostasis. Okay, and so what does that mean? Well, the bones store both calcium and phosphorus, and rather than getting rid of all this calcium, if we have high levels of calcium within our blood, do we want to get rid of it? Well, no, we want to store it. So anytime you have high calcium levels within your blood, to reduce it to normal levels, we're going to store it in the bones. And then eventually we get those normal levels once again. Now, in terms of pulling the gravity, gravity and muscles on our skeletal system, this really goes hand in hand with the second idea of remodeling, and that remodeling, it has a huge role in the support. Okay, so what does that mean? It means that eventually, right, so our skeletal system will support our entire body, and it serves as an area for attachment for our muscles and as well as an integumentary system. But our final shape of our entire bone structure is going to reflect our applied load. So the amount of weight, the amount of stress we put on our bones is going to be reflected upon the final shape it takes on. So the shape reflects applied loads, and as an example, just weight. Okay, so here we have bones. And for somebody who works out a lot, who's doing a lot of strength training, who's lifting a lot of muscle, a lot of weights to build up their muscles, you also look at their bones. And what happens over time is in an adult, we don't have longitudinal growth anymore. However, we have appositional growth. And so what do we do? Well, we can increase the width of our bones, make it more sturdy. And just think about a twig. So if somebody has twig legs versus somebody who has legs that are shaped as the size of a trunk of a tree, which one's more stable? The tree trunk, right? The tree trunk's going to be more stable. And so what is that? So how do you get from a twig towards a tree trunk? You have growth appositionally. And so this final shape of this tree trunk being that final shape of that, like your bone, that can withstand and hold more weight. Now, let's look at here, bone growth and bone remodeling. Let's see how our bones can grow in length. And it has to deal with these ideas of bone cells. We have osteocytes, osteoblasts, and osteoclasts. And so we'll first go over how the bone grows longitudinally, and we'll go over next the roles of these different cells and to help in that process. Okay, so the first area we look at here is this articular cartilage, and this is where we find at joints where prevents friction when bones come together. And so here, as this cartilage is going to grow, so cartilage is always going to grow outermost area, it's going to grow this direction. And as that grows, we can replace that cartilage with bone. So how do we do that? We're going to start regenerating more bone in this direction. Now what about this? How can we elongate our diaphysis? Well, in order to elongate our diaphysis, here is our epiphyseal plate. Epiphyseal plate is going to start increasing the amount of cartilage that it has. So it's going to start growing towards this direction, right? But at the same time, what about all of this area over here? So we can start growing more hyaline cartilage. Here is that medullary cavity down here, and then here's all that spongy bone. Well, what happens over time is all of this hyaline cartilage found down here is eventually going to get replaced by bone. So then we have spongy bone, that starts growing where that cartilage once was. But you notice we also need to extend our diaphysis, and we also need to extend our medullary cavity. So what do we need to do now? We need to break down all this new spongy bone or this old spongy bone here and free that up. So eventually what are you going to have? Here's your epiphyseal plate. Here's your spongy bone. And then here's your diaphysis. So we're going to clear this up and bring it up some more. Now you also notice here we had the bone sticking out, part of that epiphysis. We can also break this down and make it nice and long on this side. So that's what I did over here. So over time, what you can do is have this longitudinal growth. You continue to regenerate cartilage going in this direction, and then on this direction we're going to replace it by spongy bone, then eventually break down this bone. Okay, and so here we call that reabsorption. Anytime we're going to break down that bone, like here we're breaking down that spongy bone to open up our cavity space, that's called reabsorption. That's a B, and then a P, reabsorption. This is a breakdown of bone. Now I'm going to erase everything and we can go over these different types of cells. Okay. Osteocytes, these are our bone cells. Osteoblasts, the way I remember osteoblasts is that they build bone. B for B, build bone. Osteoclasts, what do these do? These crush bone. C for C. And so what does that mean? That means that here, as we're growing longitudinally, and here all the spongy bone is going to start replacing all of that hyaline cartilage. Here's our new hyaline cartilage that's been reformed. Here's spongy bone, spongy bone, spongy bone. Notice we still have spongy bone down here. We want to extend our diaphysis. So how are we going to do that? We got to break down our bone. Osteoclasts assist in this process. They're going to start breaking down all of the spongy bone over here to open up our cavity. Now on this other end, in order for us to replace our spongy bone, replace the cartilage with our spongy bone, that's when we use osteoblasts. So they're going to start to build bone. So really, in order for us to have remodeling, it's this interplay between three different characters. Osteocytes being these bone cells itself, osteoblasts, building up more bone from the hyaline cartilage, and then osteoclasts, breaking down all the spongy bone to open up our medullary cavity. Now, other ways we can have remodeling is here we're going to start cutting down and shaving off the side to elongate it even further. That's another role of the osteoclasts. Osteoporosis. Now, this is very related to this idea of remodeling and how remodeling would affect the support and shape of our cells. And so with osteoporosis, this is a bone thinning disease in which bones are fragile and can easily fracture. Okay, and so it's common in women, 50%. Over the age of 65 years old. And men, it's 20% if they are 70 years and older. So those are the population that it affects. And any time, so you have this breakdown, withering away of bone. And what are some factors that you can think of that we just mentioned that can give rise to osteoporosis? So good. So storage of calcium and phosphorus. If somebody doesn't have enough calcium in their blood or in their body, where else can we get our calcium from? From our bones. And that being the case, we're going to start crushing down. From those osteoclasts, we're going to start crushing our bones down to free up more calcium to bring into our body. This is why we also need vitamin D and to help increase that calcium retention within our body. And now if you have very fragile bones, because we don't have enough of that storage, what can happen is that these bones can collapse if somebody who has very fragile bones carries heavy weight. We don't have any of that support. And that can lead to a collapse of the vertebra, leading to what's called kyphosis. So this can appearance of having that humpback. Now, how is the treatment for this? Estrogen has been found to help give rise to the normal density of a female skeleton. So estrogen. Okay, and so with estrogen and also with more calcium, more vitamin D intake, you can help maintain the structure of that bones. But of course, what else do you need? You also need to apply some weight on your bones in order for them not to remain, in order for them to remain sturdy, right? You want to maintain appositional growth. This very last concept we're going to go over is how do we repair bone fractures. And so there are two methods of doing this. We need to know that they are reduction and immobilization. And so reduction is the act of realigning both of the ends of the broken bones and then finally putting them in place to allow for repair of the fracture is immobilization. Now this idea of repairing bone fractures occurs in 4 different steps. This 4 different steps you do need to know for your exam number 2. The first thing is hematoma forms. Here's our arterial supply, and of course we have all of those vessels feeding through our osteons. Anytime our bone breaks, what happens? Well, you rupture these vessel supplies, and what happens? Blood leaks through. And so in effect, this leakage of this blood forms a hematoma. Now what happens? Now over time we can have repair, so we're going to start repairing back our vessels, and then also all this cartilage, fibrocartilage can start forming, surrounding where that hematoma once was, the ends of both of these bones, the broken bones. And then finally we form a bony callus, and so here we can have remodeling. And so what's going to happen? Cartilage is going to be replaced by spongy bone. So spongy bone is this bony callus formation. And then eventually we're going to take in osteoclast or osteoblast. Which one are we going to use? Osteoclast. Good. We're going to take osteoclast and inner medulla, crush down, break down all the spongy bone to open up the space. But we also need osteoblasts to help build more of this compact bone and then also take away some of the spongy bone. Okay, and so eventually this is called a patch. So we form a patch, not entirely smooth where we broke that bone. Then over time we would start flattening out. Okay, and so this is bone remodeling. So hematoma, fibrocartilage callus forms, bony callus. So here is bony. Remember, always remember, you have the cartilage and then you have the bone. And then you have bone remodeling. So we take down everything else. Okay, so that's it for the first part of chapter 5, and I'll see you in the second part of chapter 5.